of this unknown linear mapping weighting matrix, WT, as well as its covariance matrix, sigma T. So what we do here is that we can represent this current belief of the ground truth linear mapping in this ellipsoid. And what we want to focus is not what we are confident about, it's about what we are uncertain about. So if we're assuming this linear mapping, this phi is in two-dimensional space, so the longer principal axis representing we have more data already collected along this dimension, and the shorter one representing less data. So in this case, when we prepare for the exploration, we want to basically take rotate this confidence ellipsoid by 90 degrees so that we can focus more on the principal axis representing dimension where we have less knowledge about, right? So in this case, we employ the Thomson sampling so that the robot could, at every round, the robot will pick up, hopefully, the dynamics represented by the linear mapping that is having less knowledge of the current ellipsoid. So once we have this sampled knowledge of the linear mapping, we can then use that as your current belief of your dynamics, and then use your favorite MPC solver to solve these particular control actions in order to optimize a objective function. And of course, we will use this stochastic setting of the control barrier function to guarantee safety with high probability during the process. And once we have these control actions policies, then we can execute it and then collect a trajectory represented by a set of state action and the landing states. And then we can aggregate the data set and prepare for the next training episodes. So let's look at an example of using that algorithm. Let's consider an invented pendulum problem where you want to stabilize the pendulum upright position. And here we introduce a safety constraint representing the condition that you don't want this inverted pendulum to hit this blue stick. So this may not seem as interesting as a running car, but they share very similar dynamics of the dynamics equations. So in this case, if we run a naive model-based reinforcement learning with the safe control, you can see because of this incorrect dynamics model, the robot or the pendulum could easily collide with this blue stick, implying the safety constraints being violated. And if we use our method, as we can see, first of all, we start with some pre-collected data, and then we introduce, and we use an optimism-based sampling method to get the linear mapping. And at the episode 0, because of the less knowledge about the robots, the pendulum is very suffering from this local minimum and not swinging up. But as the robot's collecting more data along its way, let's see episode 30, the robot is kind of like making progress towards the optimal position while always respecting the safe constraints. And when at episode 50, the robot is successful in stabilizing this pendulum without any violation of these constraints. So here we have another examples on the simple case of mobile robot navigation, where we have the robot with the initial dynamics that without knowing the actual wind field in the background, and the robots want to move in this environment, collect data, learn the wind field, and try to avoid collision with the obstacles. So in this case, as we can see on the left-hand side is our method, and the right side is a safe exploitation method. And after 10 training episodes, our method during testing is able to take advantage of this wind field downstairs that the robot have no idea beforehand, while compared to the right-hand side, the robot was stuck in some local minimum because of the lack of exploration in the environment. And we have more quantitative results in the paper. So in general, the conclusion is that in this work, we're basically focusing on using the optimism in face of uncertainty to encourage sample efficient reinforcement learning. And by combining with control barrier function, we are able to maintain safety during learning and testing. And in the paper, we also follow the proof of the bounded regret analysis, proving the theoretical results of the sample efficiency. So regarding the future work, as you can see, the robotic example is kind of like simple. It's inverted pendulum and mobile robots simulated in MATLAB. So in the future, we're interested in how to implement this method for real-world robotic experiments on more complex and high-dimensional systems. And for the limitations, we know that in our application, there's a very strict assumption that we should remain feasibility of the control barrier function, meaning that you cannot start the robot at the boundary of the safety region, that you may probably have no safe actions by that time. And the second is that we require a reasonably good initial model from the pre-collected data so that you have a roughly good estimate about the things that you don't know. And with that, I'd like to stop here. Thank you.
All right, wonderful. Don't go too far. So if I can now ask the speakers from all three papers to come and either stand around or sit at the front, as per your preference, we can start the question and answer session. All right, very good. So it seems like we already have some volunteers from the audience. So I suppose I'm in charge of calling out. Why don't you go ahead and we'll try to make sure that we keep it somewhat balanced between the talks if possible.
Hi, thanks for the great talks. So I have a question for the last presenter. So I didn't quite catch the form of the CBF. I wasn't sure if the CBF is actually a function of your current estimate of W or if it's independent of that.
So your question is about whether the current sample W is part of the control barrier function.
Wait a second. Let's see if we can get a mic that. Just a mic that we can pass around to make sure that folks can, yeah.
So, sorry, I'm asking that whether the sample dynamics is part of the control barrier function constraints.
Right. So basically, you're learning this D function, which depends on W, right? That is trying to correct for the error in your nominal dynamics. It seems like in order to be safe, you want your CBF to have some sort of a bound on how far off from the nominal dynamics you are. Is that part of it? Because I didn't catch
Oh,
that.
yes. Sorry, we didn't show that explicitly in the presentation. So yes, the learned sample dynamics is always part of the current control barrier function that you use, and that representing that how good that your knowledge are based on all the data you have seen from the history trajectories. Yeah, so.
Okay, and just a small follow-up question. When you sample W from this ball, when you're doing the Thompson sampling, is that really what gives you the bound on the magnitude of the disturbance between your learned and your true dynamics? Because the ball is bounded, or does that bound come from somewhere else?
Oh, yes, the ball is bounded. So in the paper, we mentioned that initially we are assuming you have a pre-collected data set representing initial bound of the ball, so that you just do the Thompson sampling inside this ball to remain safe and high probability of sampling these ground truth dynamics.
Got it. All right, thanks.
Yeah, thank you.
Thank you. Sorry, it's also thanks for the presentation. It's also for the question for the last speaker. So it's a very interesting approach. I was wondering, actually, two questions. The first one is like, we didn't really see the formal guarantees of the regret or the sample capacity. So I was wondering, because you are using, I'm wondering, how did you implement this optimism oracle? You are using Thompson sampling, and I guess the guarantee should be Bayes regret, but the definition you had seems to be like the high probability regret we have seen. So it seems there's a mismatch. Maybe I misunderstood.
Right. Yeah, good question. So we are not following the Bayesian settings in this case. We're just assuming that the regret is compared with the ground truth dynamics, if you know that and how optimal you could achieve this. So basically we use the Thompson sampling, and also we are assuming you have an optimal planning oracle that you can call, so that, for example, if Thomson sampling sample the ground truth dynamics. Then by using this optimal planning oracle, you are able to achieve the optimal performance. And the optimal planning oracle, what we're using is the model predictive path integral method.
I see. So I guess that's the missing part. I was wondering what's the optimism planning oracle you're using.
Right.
So second quick question is more about the comparator. So from my understanding, the CBF is like a sufficient condition to ensure like safety, but the V star is a comparator compared to the actual safe optimal policy, or it's the optimal policy that satisfies the CBF. In the regret, you have a comparator like V star.
Right. So you mean the regret between the cost and the ground truth cost?
Yeah, the ground truth is that the optimal ground truth is the one that optimal the value and also satisfy the
yes, also satisfy the
safety constraint or satisfy the CBF condition. I think they are slightly different.
Yeah, that's a very good question. So theoretically, we're assuming that is satisfy the safety constraints, but in the implementation, we use the CBF-based approach to approximate that. But you are right, there is a gap. For example, using CBF-based approach can maintain safety, but not all the safety condition could be represented by the CBF constraints.
Got it. Thank you so much.
Thank you.
Another question for the last speaker. So I'm curious how you kind of designed the feature mapping, because that seems like a kind of a strong assumption to kind of know a set of kind of predetermined features that are going to span your true dynamics. And I guess a follow-up question on that is like, how does the number of unknown basis functions factor into the kind of effective sample efficiency of your method, as well as is it possible that if you have too uninformed of a set of basis functions that you actually just can't do anything. You can't ever kind of do anything with the existing CBF that you have.
Yes, that's a very good question. So for the feature mapping, then of course we are assuming that they are representative enough to represent your dynamics. Like in our case, we use the random Fourier features in 200 dimensions of that. And you can also use the Gaussian kernels and things like that. And what we do assume is that this can be represented about your ground truth dynamics. And regarding the regret analysis, the regret will be dependent on the dimension of the kernel that you choose. So basically the dimension are there, but we don't explicitly depend the regret over the dimension of your state space or the action space.
I guess just a quick follow-up. So I guess, is there a way that, like say you have like 200 features, but it turns out that only like 10 of them are actually really relevant. Is there a way that you can detect online like which features are relevant to potentially improve like the analysis?
Yeah, so actually this can be captured by the confidence ball that we mentioned, right? So for example, if you choose 100 data point and then many of them are following a very narrow region over this confidence ball, then that means basically that kind of part may not be that relevant to others. Yeah, but we just use the standardized one and we fix the dimension. We don't do the PCA analysis and the reduced dimension, things like that.
Cool, thank you.
Thank you.
I have a question for Yazid on your paper. So on your scalability slide, it showed that your deep RL method outperformed the other methods in the shepherd path length, regardless of the size of the flock. But in your paper, you say the reward structure consisted of a penalty for obstacles colliding and breaching the payload region and a reward for the payload reaching that goal. Do you have any insight as to why the path length was that much better than the other algorithms?
So you're asking about the algorithm for the shepherding, the solution for the shepherding having 25% of the other solutions, whereas, and relating that to the reward structure of the shepherding or the defending problem?
The shepherding problem.
Okay. The shepherding, yeah, okay. So what we see that is in a lot of the algorithms that we have, the baseline methods that we're comparing against, a lot of them do like continuous actions right after you get when you get the flock to the goal to try to keep it there. Whereas our algorithm, the deep RL solution is like finding a solution where it like spreads evenly around it to maintain it there, so it doesn't move as much, and that's coming from the just keeping things in. keeping things in the goal region.